Hello kidlets, this is the first notes video for our chapter on light telescopes and starlight. So everything we know about space, we know from measuring the light or the energy that it takes for that to get to us. So whether we're looking at the sun or our nearby stars or our closest galaxy, all we can do is measure the radiation from those objects and be able to make some conclusions about those objects, even in terms of their distance. We have is the light as it hits us. It's not like we can go there. And we know that light is the fastest moving thing. So if we know how far something away is, it's essentially like we're looking back in time. So we're seeing our next closest star, Proxima Centauri, as it was 4.2 light years ago, because we're seeing how it used to be by the time that light reaches our eyes. Even the sun is 8 light minutes away, so we're seeing the sun as it was 8 minutes ago. So if we were to observe a solar flare, we'd be seeing a solar flare that actually happened 8 minutes before. As we observe light from our next closest galaxy, we're seeing it as it was 2.5 million years ago. So light is the only particle that we know that behaves as both a particle and a wave. It has duality. So we know that these waves are characterized by both their wavelength and their frequency. We quantify frequency with an F and wavelength with a lambda. And we can say that wavelength is the total height from either peak to peak or trough to trough. That would be the total wavelength, and the frequency is how many times those waves occur. So we could count how many peaks within a given time frame, and that would give us our frequency. For example, if we were to just look at this chunk right here, we could say that there is 1, 2, 3, 4, 5. Those waves occur 5 times. That would be the frequency, and the actual wavelength, or our lambda value, would be the measurable length of those waves. And we have a quantifying relationship because the frequency, how many times it occurs, is equivalent to the speed of light, which is c divided by the wavelength. And wavelengths of light have physical measurable distances. So, for example, we think of light as just being our visible spectra, but we only see visible light because it happens to fall within the physical parameters that our eyes, our receptors, can actually measure. And we measure light in terms of nanometers, which is submillimeter, and angstroms, which is also submillimeter. But certain wavelengths of light, such as radio waves, are actually so long they are measured in meters. They can actually be as long as a football field. So 1 nanometer is 10 to the negative 9th meters. An angstrom, the symbol right here, is 10 to the negative 10th, or 0.1 nanometers. So these are both microscopic. And the smaller, or the higher the frequency, the smaller the wavelength. So we know that visible light has a wavelength of between 400 and 700 nanometers, and our eyes, human eyes, are perfectly adapted to be able to see within this realm of the spectrum. However, animals and species that see in infrared can see beyond this portion of the spectrum into the infrared portion of the spectrum. So they are actually adapted to seeing different measurements, different wavelengths of light. So we can see that as we increase from our radio waves to our gamma rays, we can see that the wavelength is getting shorter. Remember, our wavelength is the total height from either peak to peak or trough to trough. We can see that radio waves have extremely long wavelengths, whereas gamma rays have very short wavelengths. But remember that frequency is the total number of times it occurs. So if we have a very long wavelength, we have a very low frequency. If we were to just separate this out right here, we can see we only have one total wave. But if we were to look at that same area over here in gamma rays, we have a much higher frequency. These occur, it looks like, about 7 or 8 times. So if we have a shorter wavelength, we have a higher frequency. So here we have a very short wavelength, high frequency. Here would be longer wavelength, lower frequency. And we can see that visible light just falls in this very narrow range right here between our infrared and our UV. And animals that see, that are able to see at night, nocturnal animals, are able to actually observe within the infrared portion of the spectra. And this area right in here gives us some really important information about astronomy. Just infrared astronomy alone gives us indicates areas of star formation, of stellar death, In fact, 90% of the universe is only viewable in infrared. So it takes special detectors and sensors to be able to see that, because we only see in this very narrow band.
You went to the setup, right?
Even within the very narrow band of the spectra that we see, we can even break apart the visible spectra into different wavelengths. I'm sure you heard in junior high about Roy G. Biv. So we know that ultraviolet portions of the spectra have a shorter wavelength, higher frequency. And as we get out towards the red, we see that frequency decreasing and the wavelength increasing. So out here, we tend towards the infrared. In the blue, we tend towards the ultraviolet. Hence, ultraviolet is past violet, infrared is just beyond the red. So we see our sun as yellow because it happens to radiate within the yellow portion of the spectra. So every color corresponds to different wavelengths of light. And each of those wavelengths has their own frequency. So aside from having one of the greatest albums of all time, Pink Floyd really did have the right idea. On the cover of their Dark Side of the Moon album, they show a prism that is breaking apart white light into each of the component colors. And the reason is that a prism acts as a refractor and slows down each of the wavelengths of incoming light into individual waves. So it breaks apart incoming white light and slows down the red, but not as slow as it slows down the violet. So we are able to see it broken up into a rainbow. This is what raindrops do as well, and this is why you see a rainbow after it rains, is because all of the water droplets in the atmosphere are changing the wavelength of light. They're slowing it down, but each wavelength gets slowed down at a different speed. So it breaks it apart, so we're able to see the full spectra of the rainbow. And because each different wavelength of light has different degrees of transparency, our atmosphere is transparent to some wavelengths and not to others. And this creates these atmospheric windows, which protect us in a lot of ways from incoming galactic rays and incoming solar rays. So we know that visible light is able to penetrate our atmosphere because we have an atmospheric window there. Radio waves do as well. So these wavelengths are able to reach ground level. We have partial transparency to infrared wavelengths. So near infrared is nearly transparent in our atmosphere, and it's almost able to penetrate the ground, whereas our far infrared is not. So with high-flying aircraft, we are able to observe in the infrared. Ultraviolet, X-rays, gamma rays are nearly entirely blocked out by our atmosphere, so those don't hit the Earth's surface. So those would have to be, these astronomies would have to be done from space. And we can see that our radio waves physically have the longest wave. They can be up to 1 kilometer long. Whereas gamma rays are incredibly small, which means they have a higher frequency, so these would be approximately the size of an atomic nucleus. So because we have these different atmospheric windows, this allows us to do astronomy from different places. This means that some astronomy has to be done from space and others can be done at ground level. So we can do visual wavelength astronomy from the ground, we can do radio wave astronomy from the ground, but things in the infrared would have to be done from space. This looks like Spitzer right here, and I believe this one is Chandra, which is observing in high frequency radiation and would have to be done outside of Earth's atmosphere. So here are some different telescopes. We have that optical window in which all of the visible wavelengths penetrate. We have that radio window. These are long wavelengths, so that's a very large window. We'll see what those telescopes look like later on in the unit, but you can see that it actually looks like a satellite dish. That's because those are larger light collecting vessels. They are literally a dish that's collecting waves, not necessarily a lens collecting light. So here you can see a plane. This is called SOFIA. There is one stratospheric orbiting observatory that observes in the infrared. This is actually launched out of Palmdale, and your teacher may be flying on this in one of the next missions that it does. This guy would be Hubble. This would be Spitzer that observes in infrared. We have the Compton or the Chandra X-ray Observatory and Compton Gamma Ray Observatory. And each of those different astronomies give us different degrees of information about space.